Now I'd like to get into some more concrete concepts and some kind of actionable tools that should help you begin to go from words to numbers. Because in the end, if we want to do some kind of quantitative analysis, we need to transfer words into numbers. A priori, you may think that's a pretty simple process, but as we'll see, there's a number of significant obstacles that often deter the person who's new to this field from getting in. A lot of people get tripped up in one of these first steps related to things like character encoding or regular expressions and some of the key concepts we're about to go over. So the first challenge to produce a quantitative data set from text usually involves text cleaning. Really fun stuff. You may remember, if you were following along yesterday, we produced some data when we were screen scraping that had some carets and single letters and some slashes and single letters, and I mentioned at the time that those are HTML tags. Those are instructions to a web browser that allow the browser to determine how and where to put font on a particular part of a web page. And so it's very common, if we collect data in that way, to have messy text with a lot of HTML tags. And so one kind of common task that you might find yourself doing in a text analysis is dealing with that type of stuff. You may also remember when we looked at the Twitter data, there was some bizarre kind of unintelligible text that I told you represented an emoji. An emoji, of course, is something that is a new type of language, you could argue, right? I mentioned at the outset that language is always changing. Well, because language is always changing, we need increasingly sophisticated methods of encoding language and strings in a digital format. And that is the beauty, the sheer beauty of character encoding. Character encoding refers to a process of capturing all types of human language or all types of human letters, again, into digital format. And here you're looking at some examples of a few, but maybe you've saved an Excel file and you've been asked whether to save it as UTF-8 or Latin 8 or something like that. And what that is a set of instructions you're giving to, in that case, Excel, about how to save the data. Why do you need to give specific instructions? Well, suppose your text is only in English, contains no emoji, and is a fairly straightforward English document. You may be able to get away easily with one of the earlier versions of character encoding. But now suppose you've, like I did, collected all mentions of the hashtag Korea, and some of your text is in English, some of it's in Korean, some of it's in Chinese, some of it's in German, and now you need a way of representing digits or characters that can handle umlauts, characters, Chinese characters, and emoji, right? And so typically we struggle to find a single format that can capture all these things. Some are better than others, but very often if we're trying to coerce one set of text into another thing, like reading it into R or moving from one style of spreadsheet or database to another, we wind up confusing the character encodings, and we're left with our current tool, whatever we're using. Maybe today it'll be RStudio, but again, if you're using Python out there, great. You may discover that an emoji doesn't get rendered as an emoji in your RStudio data browser. It gets rendered as this unintelligible text. And in many cases, you may be content to just say, I don't care about emoji, emoji aren't that important. Of course, we could have a debate about, like, for example, the cases we were talking about yesterday were things like studying health behavior among teenagers, and one can imagine, eliminating emoji could have serious consequences there. On the other hand, for other types of analysis, or perhaps you're working with administrative data where emoji aren't even possible, you may think, that's not something I have to worry about. Unfortunately, even in those cases where you're, say, combining historical text collected across multiple periods, let's say you've got administrative records going back 60 years, you may find yourself in the environment where 1930 to 1950 documents were using one character encoding, and 1960 to 1980 was using another, and so on and so forth. So in other words, very often the first task in doing an automated text analysis, even before you can clean it, is to figure out what the character encoding is, or to at least standardize the character encoding into one and only one character encoding. Unfortunately, it's a relatively tricky problem to guess the character encoding of a string for which you don't know the character encoding, and very often you won't know the character encoding. And so one solution is to use a utility in R called iconv, I-C-O-N-V, which allows you to coerce one set of character encodings into a single character encoding. So you could use that function to, for example, take texts that were in 5 or 6 different character encodings and coerce them into the UTF-8 character encoding. That may work very well in many or most cases, but if some of the characters you eventually want to read were in one character encoding and not another, or somehow got confused in that translation process, you may still wind up with unintelligible characters in your text. So getting a handle on character encoding, and one of the first things I often ask people when they say they want to do a quantitative text analysis is, what type of format is your data in? And if someone tells me, Microsoft Word or a PDF or something like that, the very first thing that comes to mind is, oh, there's going to be some headaches here around character encoding, particularly if they're in different formats. But also if people are scraping multiple websites, or again, looking at multiple historical periods. Very often, if you take a class like this, you begin with a very well manicured and curated text database, like the popular ones are like the State of the Union addresses, or there's large databases that describe every news article from the news organization Reuters, and essentially you get a very easy to use set of data. And so it's important for you to understand these common pitfalls, because your data, if you want to make something new and don't want to study one of these well-formed data sets, will likely have one or more of these issues. Okay, so now that we've gone over the concept of character encoding, I want to briefly introduce grep, which is a very old tool but very useful tool for cleaning up text. So I mentioned at the outset, you may have HTML tags in your data. Here we're seeing an example of a few of these. These are tabs. This one means put a new line. This is from the data we collected yesterday when we talked about screen scraping from the duke.edu site. And though we got what we wanted at that time, which was a description of events happening at Duke, we got all this other junk. So fortunately, for some time, this language grep, which is, again, predates RStudio by quite a bit, allows us to go through and do things like find out whether, in this case, using the grepl function, whether the, whether a term exists within a character vector. This is the character vector and this returns a Boolean statement, true or false. We can then use that and put grepl within, say, a database subsetting command to identify problematic rows within our data set. And we can also use commands like gsub, gsub, the function gsub, to identify one character and replace it with another, and I'll show you how to do that in just a minute. So, for example, let's say we wanted to remove these /t's here. What we're saying here is identify this pattern and replace it with this pattern, which is nothing, and apply those instructions to this object. So if we do that, we'll see that we were quickly able to get rid of those /t's. We still have our /n's, but we could add an or operator and a /n there, or we could repeat this instruction with other HTML tags, or fundamentally, there are better ways to do this. I'm right now trying to show you the kind of building blocks of working with text, but I'll show you later a variety of tools that do this type of text cleaning for you. So there's packages like QDAP or several others in the R framework or NLTK in Python framework that would allow you to systematically remove HTML tags by looking for patterns like slashes and carets and arrows and stuff like that. So you may not want to do this eventually. I'm simply trying to get your kind of muscle memory going with text analysis, because there likely will be cases where you want to transform your text in some way. So here's an example of how we would add on that additional condition, and now we have our clean text. So grep is particularly useful for identifying more elaborated patterns in text. So here we're using this wildcard operator to look for any word that begins with P. Why are we putting brackets in this upward-facing caret here? These are regex instructions. I'll explain and show you how to look up all of those and what they mean, but essentially it's a way of telling grep, or RStudio in this case, how to look for something, what pattern to look for. And patterns are represented by these type of abstractions. So we can look for things like words that begin with P, words that end with P, words that contain a number, and all of these types of things can be helpful in your first pass of a text analysis, because very often if you're looking for words that have, for example, been mistranslated via character encoding, you may want to discover all words that contain, punctuation marks or something like that. And then take a look at them before you begin to think about moving into a database. This is a very helpful cheat sheet that the RStudio team has put together for regex. And these will allow you to kind of browse a lot of different types of regular expressions. I just gave you one example in the previous slide there, but this cheat sheet will allow you to determine, for example, how to identify lowercase characters, uppercase characters, various types of punctuation, all sorts of functions within the grep language and within other very useful packages for text analysis in R, like string R or string E, or QDAP, which I mentioned earlier, and ways for looking at and creating Boolean statements or true-false statements that you can then pass into your code to subset text in various ways. So bookmark that if you're working in R. Should also say that if you're coming from another language to R, you can set the convention for grep and regex in R to different languages like Perl or C. So if you're familiar with other conventions, you can set that as a default in R by adding in the grep family of functions statements like Perl equals true. And as always, if you want to look into the documentation for any R command, you could write question mark and then the name of the R command and then open and close parentheses. And that's where you can get information like that. Another common problem is, okay, so I found something that I don't like in my text, and I want to get rid of it. For example, something like these, these brackets, and the problem is that sorry, I've got an error on that first slide there. But this slide, what I'm telling R to do here is remove the brackets from this statement, from this character vector here. This professor is not so great. I want to get rid of these brackets. So the issue here is you might think I can just do a G sub and put those brackets in and then replace them just like we did with the /n or the /t. The problem is certain characters have a meaning to computers independent of what they mean to us. So things like these brackets in R are used for subsetting data frames, right? So we need to have a way to tell R, or whatever language we're using, to escape those characters, meaning treat them as characters, not as instructions about how to execute code. And so there's different conventions for doing this in R. One is to use these slashes and vertical pipes around the character. Another is to use a sequence of single and double quotation marks. But this is one of these frustrating things you might spend 5 minutes Googling around on Stack Overflow, particularly trying to figure out exactly how to escape your text. And that can just be another problem that deters new people to the field because they don't even know that they need to escape text. So this is just another thing to keep in the back of your mind. You may have a character encoding problem, you may have HTML tag problems, and you may have issues with escaping text. Okay, so those are some kind of 3 basic ways of thinking about cleaning text. And your goal here is to produce language that is as close as possible to what you want to run your analysis on, what the content that you really want, getting rid of all the junk that a computer might create, for example, in the process of scraping or even mining data from an API. The next question you have to answer is what's going to be your unit of analysis? So when we're thinking about text, we could begin to think about a lot of different ways of analyzing the text. I mean, we could read the whole thing, we could count each word, and there's a variety of different types of units of analysis that we could consider in between. And this process broadly refers to how you're going to tokenize language. So here we see text that's tokenized by sentence and by word. Linguists, for some reason, love this brown fox business. But basically what we're seeing here is, we can decide to chunk up our text by words, by sentences, or by what's known as n-grams. And these are simply sequences of text of length n. They could be unigrams, that would be a word. They could be bigrams, that would be sequences of 2 words. They could be sequences of 3 words, that would be trigrams. And so here's some examples of those 3 things in this sentence. So basically, why would we want to capture n-grams instead of unigrams? Well, there's a variety of cases where sequences of words may have a different meaning than the individual words themselves. For most of the analysis we're going to do today, and for much of the field, people simply assume that unigrams are the most useful unit of analysis and drop all of them into what's known as a bag of words, meaning we analyze them kind of independent of word order. There's been some recent research that shows that there's some consequences of making that assumption, and I'll talk a little bit more about that later. And there's also new tools for extracting sequences of words that have particular meanings, like named entities or geographic places that you might want to treat differently than unigrams, and we'll talk about those later as well. But just so you know, if you see the term n-gram, this is simply referring to a way of chunking up text into units of analysis of length n. It could be 1 word, 2 words, 3 words. So the next challenge is to think about how to actually create a database, how to go from the unstructured text. So by now, maybe you can see your text in your RStudio session or in your Jupyter Notebook or whatever you're using, and you can read it, right? But you sure can't run a topic model on it or a regression model on it if it's still just a chunk of text, right? Eventually, we have to go to some type of matrix representation of our text. And so what we're working towards now we've talked about cleaning and about creating unit and defining a unit of analysis, now we have to think about how to take our clean text with our given unit of analysis and produce some type of matrix representation of that text. So typically, the most common way of doing this is to create what's known as a corpus object. A corpus object is a data structure that both can capture the full text of any kind of text database. So if you've got lots of news articles, it can capture each article. It can perhaps also capture metadata about that article. So when we talk about structural topic models a little later today, we'll see why we might want to have metadata attached to our text that might help us improve classification or run other types of analysis on our text. But also, we need some matrix representation of the text. And so a corpus object in R is a type of data structure that includes both metadata, full text, and eventually a matrix representation of that data. And I'll show you what that looks like in just a minute. But first, let's look into creating a corpus. Here's the data set that we're going to use in our group exercise later today. We spent all yesterday with Democrats on Twitter, so today we're bringing in the Republicans. We're reading in here a data frame, an R data frame from my GitHub that's simply about 20,000 tweets by President Trump from, I think, about 2017 to 2018 or thereabouts. And this is what the data look like. You can see it's a little messy. We've got some hyperlinks in there. We've got some @mentions. We've got some hashtags, and so on. And so it's not quite the easiest data to work with a priori, but I just wanted to give you a quick heads up of how the things we were just talking about, things like character encoding and other types of terms may come to factor in your analysis. So for example, when we're thinking what we want to put into our representation of text, our matrix representation of the text, do we want this arbitrary URL that Twitter assigned to a Trump tweet? Right? We could make an argument that if everybody's talking about that URL, then that URL adds some meaning to our classification of the text and we should keep it in there. On the other hand, it could just be literally a random chunk of strings for our purposes and we might want to drop it. So as we go through the steps of creating and building, getting to our matrix representation of text, we're going to have to make those types of decisions. And I'll try to offer you some useful standards, but more often than not, I'm going to encourage you to make a decision that's best about your data. And early and often, one thing I really can't emphasize enough when working with text data is you need to browse your data very often. Almost everyone who experiences initial hiccup in text analysis is trying to perform an analysis on their text that they themselves haven't even seen. So maybe you've got rows of missing data, maybe you've got a character encoding problem, maybe you've got a character escaping issue, and you just need to look at your text to diagnose these things. Now, a key problem, of course, is if you're coming to the field of quantitative text analysis, you're probably doing it because you have a really large amount of data and you don't want to read it all. But even just a cursory kind of browsing of the data can help you diagnose some of these problems, or at least look at where your code is breaking as you read things in. So in R, one of the kind of workhorse packages for text analysis is the TM package. We're first going to work through a case of using the TM package to create a data structure called this Corpus data structure. Then we're going to work through a newer type of matrix representation of text called TidyText, which has some advantages that I'll discuss in just a minute. But I want you to know both in case you want to, in case you're working with data that comes from one set of origins or another. So here's a technique for reading in characters from a data frame. So the data that we just downloaded are in data frame format. They're rectangular already. They're not in a Word document. They're not in a PDF document. And we can simply use this Corpus function with this somewhat verbose and lengthy argument here, or sorry, a sub-function here as dot vector, which is telling this Corpus function that our data are in vector format, meaning they're a vector from a data frame. And we're creating a new Corpus object called Trump Corpus. And if we browse that, we can see we've got, oh, sorry, there's 3,196 documents, not 20,000 I mentioned earlier. I got confused. And we see some metadata as well. Not a lot, but a little bit. So that's what a Corpus object looks like. Now we're going to talk about what a TidyText object looked like. So one challenge of working with Corpus objects is that they have this complex structure, right? You've got all these moving parts. It's kind of a complicated structure to navigate. If you want to do somewhat basic things like count keywords or remove certain characters, you need to use functions that are specific to the Corpus family in order to work with them. In contrast, TidyText takes a different approach. It divides each word in a document into a row in a data frame. And so all text can be described simply in a data frame. The advantage of that is that all of the tools that you're used to working with data frames, like subsetting a data frame, or if you like dplyr, or if you like ggplot, there's no going back and forth and creating intermediary data objects in order to do that. One downside is if you have a very long corpus with many different words in many different documents, and each word from each document is a row in your data frame, in your TidyText data frame, then you're going to have a huge database. And depending on your computing resources, that could become challenging. Though the folks who build this package as well as dplyr have become much more sophisticated in creating infrastructure to support relatively large data sets. So I recently worked with a TidyText data set that had 26 million rows natively within this machine, and I was just fine. Okay, so here's what a TidyText representation of a text would look like from our Trump tweets. If you are new to R, you may not know what these pipes are, this little snippet of code here. And maybe you use R, but you don't use the tidyverse or dplyr. This is a very popular language for data wrangling, package for data wrangling. And essentially what these pipes do, but maybe if you're from Python or another language, you recognize pipes. Basically what we're doing is passing the output of any line to the next line. So here we're taking our Trump tweets data, we're selecting one variable, created at, which is the timestamp or time in which the tweet was created. That's a unique identifier for each tweet in this text. And we're taking out the text variable there. So we're basically in this code, we're simply selecting the data frame and the part of the data frame that we want to turn into a TidyText object. And this is the workhorse function of the TidyText package, unnest tokens. What this is doing is taking a really long tweet, like the first one in our database is just met with UN Secretary General Gutierrez, and instead of representing it as one long character string for each tweet, with each timestamp, so you can see these first 6 lines of the TidyText data all have the same timestamp. This is when the tweet was produced by Trump. And then each line has a word from that tweet. So we have a unique row in our data frame for every single word from every single tweet in the order in which they appear. Another useful thing about this TidyText representation of text is if we have metadata, like for example, additional details about the political party of the person speaking, or let's say the way the data was collected or something like that, we can simply add additional rows here. Whereas in the Corpus object, it's a little trickier to put those in metadata. So the advantage is TidyText is tidy. So basically, as I mentioned earlier, we can use dplyr commands, or really any kind of command. If you don't like dplyr, you could also use base R to navigate and subset and transform your code. But basically, we can go from this tidy Trump tweets object that we just created in the previous step. That's our really long database now that has a different word from a different tweet on each row. And we can do things like count words with just a few lines of code. So that's handy, and it's it's kind of like we say in the States, different strokes for different folks. Whatever you like and find more intuitive is what you should do. If you're in another language, I'm fairly certain TidyText is, or something like it is not yet available, but there are other alternative data structures and other workflows that you can explore in other languages as well. You'll have to pick the one that works best for you. It will be a function of whatever language you feel most comfortable in, the type of data you're working with, and the type of analysis you'd like to do. So for example, if you'd like to do structural topic modeling, which we're going to learn about in a little bit, that's not yet available as a Python library. On the other hand, there's various types of Python libraries and modules that are not available in the R framework. If you are well versed in either of those languages, though, you can call Python from R, or in many development environments do the opposite as well. So, I encourage you to learn one of these workflows well. Typically speaking, you'll be able to find and develop a workflow that will allow you to, for example, if TidyText is really intuitive to you, you can probably go from just about any word representation and character encoding into a TidyText data set with a bit of work. And there's a really excellent book and free online book and tutorial on TidyText written by Julia Silge, who's a data scientist at Stack Overflow. And I highly recommend that book if you really are kind of taken by TidyText. So that's the kind of key decision. Corpus is much more familiar to many people. I would say broadly speaking, most people are using corpuses, but increasingly, particularly within R, lots of folks are using TidyText because they provide this somewhat neat or familiar representation of text-based data. Okay, so I want to go back quickly and take a look at these top words that we found in the Trump tweets. The, to, and, of, HTTPS, t.co, which is a way that Twitter creates shortened links, a, in, is, right? None of these words are going to be very informative in our analysis. It's not surprising that they're the most common word, but the fact that one Trump tweet has the word the and another one has the is going to be very unhelpful in helping us kind of pull out some signal from all the noise and unstructured nature of text-based data. So one of the next steps that we're going to do is we're going to make a variety of choices about how to further constrain the unit of analysis as we continue our magical journey to the matrix representation of text. Okay. The first thing we have to do is make decisions about those types of words, the, to, it, and, he, she, and so on and so forth. These are very common words that are often called stopwords. These are words that appear so regularly in text that we very often make the decision to drop them. because the fact that they appear in most every text, or in our case, most every tweet, makes it really difficult for any type of algorithm to make a decision about how to categorize it. If it appears everywhere, it might as well appear nowhere. That's the kind of bet that many folks in NLP have made for many years, and it's become very commonplace to drop stopwords from an analysis. Obviously, if you're working in a language outside English, you would have a different set of stopwords, and in other languages, there won't be any stopwords at all. And if you want to work in a particularly rare language, you might have to come up with your own list of stopwords. And you may even decide that there's additional words that just appear so often, like for example, in the case of our Twitter data, if someone says Twitter a lot, right, that doesn't really help us categorize the data either. And so some people will use a benchmark, like if a word occurs in more than 95% of documents, then we should drop it. We'll see a tool that does that in a little bit. But really, I encourage you to know what's being dropped. And so if you want to browse stopwords, I'll show you how to do that in just a minute, but they are mostly prepositions and articles of speech that, again, don't add much meaning. So if you're working with a corpus style object, this is a function, tmmap, that has an argument called remove words. And it, like many R packages, contains some data in it. So if you went to the folder where your R packages live on your computer, you would find a small data set called English stopwords. And this is just simply calling that list of words. These are the words I just started to mention, the, to, it, and, he, her, she, and etc. And then transforming the corpus so that all of those words are removed from the analysis and they're not going to be in our matrix or data quantitative representation of the text. In TidyText, it's very similar, except instead of using these two functions from the corpus package, we're simply going to use a merge command from dplyr. So here we're using the anti-join command, which takes all the words in this object and removes them from this object. And we're using pipes again to pass that along. And this arrow here is saying, or this assignment operator here is saying that we're creating a new data structure here. If you're not very familiar with pipes, and this is your first time seeing them, I promise they get a little easier as you begin to work with them a bit, but maybe come back and try to work through this later rather than getting too focused on what's going on in this code. Essentially, we're doing a dplyr style merge that we could have written out in individual line of code, but we're using pipes as a kind of shorthand to arguably make our code more elegant and efficient. So now we can inspect the top words again. We're doing a little bit better. We still have HTTPS here. We still have t.co. We still have AMP. We have RT here, which is going to stand for retweet in many of these cases. And probably all these words would be candidates in many analysis for dropping as well, because they're simply not adding a lot to the analysis. But people, news, president, fake, Trump, now we're starting to see words that are characteristic of President Trump, and we might actually want to analyze. So we're getting there, but there's a lot of other non-trivial decisions we have to make about text pre-processing, about how we're going to further constrain the unit of analysis that we're eventually going to study in our tweets. So another decision, for example, is removing punctuation. This is how we would do it in the corpus style object. There's another function within the tmmap function called, or another function that can be called by the tmmap function, which is called content transformer. And this particular one removes punctuation marks, so commas, dashes, em dashes, quotations, and so on and so forth. And the thought experiment we need to do here is there ever a case where punctuation marks are going to change the meaning of a text? And the bet of many people in the NLP community is no. It's very often not going to change the meaning of a text. But we can imagine cases where it might. Like, you might say, like, let's eat, Dad, right? Like, we're going to go eat. Or you could say, let's eat Dad, like meaning like, let's consume Dad, right? A comma there is profoundly changing the meaning of that sentence, right? The decision there to remove punctuation is non-trivial. But the bet is that that type of data structure, that type of word structure, is far less common than the simple meaning of a comma that's breaking up independent clauses or phrases in language, right? So it's become common practice to do this. There's a new working paper by Ron Breiger and John Moore and Robin Wagner-Pacifici, which suggests there are consequences to removing punctuation for various styles of text analysis, but that's hardly the end-all, be-all analysis of this issue, and the vast majority of people continue to simply remove punctuation. The other decision is to remove numbers or not. Very often, you might get numbers that describe dates or, I don't know, individual document identifiers or the number of people who were, say, killed in a news article or something like that. And sometimes those numbers can carry meaning, like in the U.S., if we were talking about 1776 there are numbers that convey meaning independent of by themselves. But many numbers, most text analysts would argue, don't add much. And so it's become very common practice to remove numbers. So here's how you do that with a corpus style object, and here's how you do that with TidyText. I forgot to mention that punctuation marks are removed automatically in TidyText, and you can turn that default behavior on and off in the unnest_tokens function, which is the function that splits up a character string into individual rows of data. Okay. We also have to make decisions about word case. So if we have a word that begins at the beginning of a sentence and in the middle of the sentence, it might be capitalized if it appears at the beginning of the sentence, but not if it appears in the middle of the sentence. And for many words, that probably doesn't matter. For other words, like for example the word God, if someone capitalizes the word God or uses lowercase, it could convey something about the speaker or the writer, right? That they're a religious, more or less religious person. So again, there's some debate about whether this is a reasonable choice, but once again, the common practice in the NLP community and in computational social science broadly has been to ignore word case, which means that we transform all words into either lower or uppercase, and usually lowercase. So this is how you do this in the Corpus package with a corpus style object using the tmmap function. And once again, TidyText does this for you. Another really annoying problem. Remember that one of our initial challenges in thinking about reading in text data was that they can have different types of data structures that underpin the actual characters that we're seeing, the character encodings. Well, to us, 2 blank spaces is something to ignore. But to many text analysis programs or to many data structures we're using, 2 blank spaces has a different meaning than a space. Or a space before a word or after a word can actually be a different word. So often we want to make sure that we don't have spaces that are getting counted as words in our analysis, strange as that may seem. And that can result from different conventions in whether people use multiple spaces or accidentally added another space and all this kind of stuff. So here's how we get rid of extra spaces in the corpus object, and here's how we do it in the TidyText object. Finally, we have to make decisions about whether or not to reduce all words to their conjugate or most basic form, or allow plural versions or various conjugations of a word. So if I have the word running, and let's say I have a corpus of text that's about exercise, you could make the argument that the word running, ran, and run all basically have the same meaning, right? Someone's running. And that's all we really care about, that someone's running. But remember, as we go from words to numbers, every unique word, every unique character that's appearing on your screen is going to be treated as a different word. And so a very common step in text analysis is to reduce all words to their most root form using either a process known as stemming or lemmatization, which is a slightly more sophisticated technique. But basically stemming is straightforward in either the corpus style object up here or in the TidyText package. TidyText is going to call a package called snowball-C, which is going to use something called the Porter stemmer. This is a tool developed by linguists which uses a database to reduce all various transformations and extensions of words into their most root form. So both of these chunks of code would take the words running, ran, and run and make them all run, R-U-N. Sometimes they would be they would add an asterisk at the end of run, which describes words that might have any text that follows after RUN. So running and run would be described as RUN asterisks. Okay, so we've now gone through a lot of different steps. This isn't the most exciting stuff, I know. We're getting to the fun stuff soon, but I promise you if this is your first introduction to text analysis, you'll appreciate all of this kind of messy data cleaning stuff. We've gone through character encoding, we've gone through text cleaning, we've gone through text preprocessing, we've talked about the unit of analysis. I want to pause and see if there's any questions in the room or from the live stream about any of this stuff. Okay, so we're gonna mix up the schedule just a little bit. We are going to, I'm gonna hold off on that question. Brandon is now outside, who's going to talk about topic models, but before he comes in, I'm just going to take you through the last section of data structures so that we can move on and understand how topic models are working. So I've been saying all along, we've been working towards some type of matrix representation of text, and we need to have a matrix to run a topic model. We're going to circle back and talk about dictionary methods later, which are a somewhat more primitive form of text analysis that relies upon counting the appearance of different words labeled in a dictionary. But now we're going to talk about creating the data structure necessary for topic modeling, and this data structure is called a document term matrix. Sometimes we call it the DTM. And basically what we're doing is creating a rectangular matrix where the rows are different documents, and the columns are every word that ever appears in any of the documents. Then the cells of the matrix describe the number of times each word appears in that given document. And so this allows us to have a very efficient representation of a document of a set of documents in what we call the document term matrix format. So here's some code that helps you do that in the Corpus style object. And here's some code that helps you do that in TidyText. You can see essentially what we're doing here is using dplyr to count the top words in the data set, and then we're using a cast or data transformation technique to go from our long TidyText representation to a rectangular representation that describes the document term matrix. Okay, so most of what we're going to be doing, Brandon's going to come down in a few minutes here, and we will start to see the document term matrix in action. But basically what we've done here this morning, clean our text, pre-process our text, decide upon the unit of analysis. We've decided upon unigrams for now, and we've created an efficient data structure that represents words that appear in our corpus, in this case of Trump tweets, we've removed very common words, we've reduced words to their most basic or conjugate form, we've removed punctuation, we've removed numbers, and our bet here is that we have all the words in our document term matrix that are likely to add the most meaning and carry the most meaning, and we're going to pass those now to various types of models to try to pull out latent themes and structures in that data. So shall we take a break, or should we, let's do a 5-minute break. We're running a little bit behind schedule. Apologies for that. And then Brandon's going to come back and talk about topic models and structural topic models. Thank you.